My name is Tim White. I'm a system architect with Integrated Device Technologies, and I'll be talking about the advantages of sensor conditioning using the CENT interface. I'll cover three topics. I'll give an overview of the CENT 3.0 protocol, how CENT can be a good alternative to analog output, and some sensor applications using the CENT interface. CENT stands for Single Edge Nibble Transmission. It's an output-only digital interface. So because it's output-only, it's really not an alternative to LIN or CAN in an automotive application, but is seen more as an alternative to an analog output. And just like an analog output, in a sensor module, you typically only need 3 wires: the SIN output, power, and ground. There is one restriction on CENT, that the power supply needs to be from 4.75 to 5.25 volts. And the encoding scheme is variable timing between 2 falling edges, and we'll talk more about that in later slides. There are 2 ways to transmit data on CENT. One is using fast channels to bring out the primary sensor information, like pressure or throttle position. But there's also in the background a slow channel message that can be transmitted and allow you to bring out things like diagnostics. On the fast channel, there are 3 formats: the standard format, single secure message, and high-speed message format. And also on the slow channel messages, there's 3 formats. The short serial message is when you transmit 8 bits of data, and then 2 enhanced serial formats where you can either transmit 12 or 16 bits of data. So the fundamental unit of measurement, time measurement for CENT, is the tick time. The minimum period is 3 microseconds, but it can be up to 90 microseconds. A second timing notation is called the nibble. And from the diagram, you can see a nibble is from falling edge to falling edge with a fixed low time, and then you vary the high time to represent different values for your data. So in this waveform, you see the first fast channel message called the standard format, and it brings out 2 fast channel messages, each are 12 bits. But it starts with a synchronization and calibration pulse, a status and communications nibble, then the 2 12-bit data words, a CRC and checksum, and then an optional pause pulse. And here you can see a little bit of how the nibble format works. So to represent 4 bits of 0000, you would have a fixed low time. It could be 4 ticks or 5 ticks or 6. It's programmable, but once you set it, it stays at that value. So typically we would set the low time to 6 ticks, and then the high time would also be 6 ticks to represent all zeros. Then to represent a data value of 1, you would increment to 13 ticks. Then for data 2, it'd be 14 ticks, and so on up to, here you can see in the second nibble, 27 ticks would give you a value of 15 or all ones. The second fast channel format is called the single secure message. This one also starts with synchronization pulse, then the status nibble, followed by 12 bits of data, then a 8-bit counter that increments from 0 to all ones and then rolls over back to all zeros, the inverse of the most significant nibble, a CRC, and then a pause pulse. The third fast channel messaging format is called the high-speed message format. And here you can see that the data is coming out in as 12 bits, but it comes out in 4 nibbles instead of 3 nibbles, with only 3 bytes represented. And by eliminating the most significant bit in each nibble, it does narrow the overall pulse width so you can get faster data throughput. And this also has a slightly faster tick time than standard. It's 2.67 microseconds. Now for the slow channel format. So this first one is the short serial message format, and this brings out 8 bits of data. And if you look at the way it's organized in the status and communications nibble, you can bring out only 2 bits of data in each message frame. So this means to bring out 8 bits of data requires 16 message frames to bring out the 8 bits. And included in the 8 bits is a message ID, the 8 bits of data, and a 4-bit CRC. Additionally, there's a hard-coded value in the bit 3 location. It's 1 and all zeros. And the idea there is every time you roll around to a 1, you know that's the start of the next slow channel message. So the fixed 1 with all zeros is a way to know when each slow channel message begins and where the next one ends. Now the other slow channel message format is called the enhanced serial message format, and it's the same format here, but you can either option it for 12 or 16 data bits. So looking at the 12-bit format, there's a configuration bit shown here in magenta. If it's set to a 0, then that is 12 bits of data coming out. And this one requires 18 message frames to bring out the 12 bits of data. But included with that data is a 6-bit CRC and an 8-bit message ID. And in addition, you have some fixed 1s and 0s, again, so that you can identify where each message begins and where they end, so that you have an idea of where you are in the transmission. Also, a comment on the message ID. This is unique for each vendor, but is somewhat becoming standardized. And this allows you to look at the message ID and know whether it's a temperature, a diagnostics, production code. The message ID tells you what piece of information is in the slow channel message. Then for the enhanced serial message, 16 bits of data. Very similar. It still takes 18 frames to bring out the complete message. But here you have 16 bits of data, a 6-bit CRC. You only get 4 bits for the message ID. And for this option, the configuration bit is set to 1. Now here you can see an oscilloscope trace of the scent transmission. So there are scopes now that do decode the scent protocol. There are also scent decoders that you can order on the web that allow you to decode the scent signal, and microprocessors now are starting to develop digital decoders as an interface for scent, but you can also oversample the scent output with an A to D converter and build your own custom decoder. Now as far as the scent format, when the original J2716 specification was written for scent, the format was defined based on applications. So how the data comes out depends on your application, whether it's throttle position, mass airflow, pressure, or high temperature sensing. And I've included a table here to show what the different formats are for bringing out the data. So in some cases there's 2 channels, in other cases there's a single 12-bit channel, whether it's the standard format or the single secure message. So you can look at this, and this tells you what the format should be for different applications. Now I won't take time to go through it, but I have a table showing abbreviations and some of the scent terminology. So it gets you used to the terminology for scent and some of the key points about how to format the scent protocol. Okay, now after the terminology, I'd like to talk a little bit about scent versus analog output. So first of all, scent is a full half duplex digital interface, so it is output only. And so when you power up your sensor module, it just continually transmits data, which is a big advantage in safety critical applications where you cannot interrupt the sensor data from coming out of the module. It also is similar to analog out in it has the 3 wires, power, ground, and the scent output. The nice feature of scent too is it has very overdamped rise and fall times with very controlled timing. So this reduces harmonics and really helps with emissions. It also can put out up to 16 bits of resolution, where with most analog outputs they're limited to 12-bit accuracy through the DAC or through the op-amp. The analog output also has a limitation in that it's usually only able to put out one piece of information, and if you want to put out more than one piece of information like pressure and temperature, it requires a fairly elaborate scheme to decode, where with scent you can bring out up to 2 fast channels and 32 different slow channel messages all in one transmission. Another interesting thing about scent compared to analog out is it has the same features you're used to seeing in an analog output in an automotive application, where you can set a lower and upper diagnostics range. You can set clipping limits to have the output clip at the low end and the high end. And you can also set the linear range. And you can record in the part your X1, X2 values for linear range. That may be from your pressure range from 0 to 100 psi, for example. And then your Y1 and Y2 for the linear range, where you can define the count or whatever parameter percent of full scale. These can actually be stored in the part and read out as in the slow channel as a slow channel message. I've included a block diagram of a typical scent sensor signal conditioner. So here you can support, this is supporting 2 bridges, 2 external temp sensors, an internal temp sensor, and through configurations on the part you can bring out any combination of these bridge values or temperature values through the scent output. So it allows for a lot of versatility on how your output is formatted. Also, scent does support overvoltage reverse battery, although it's not defined in the standard. The industry standard is typically around plus or minus 18 volts overvoltage reverse battery on the supplies and on the scent output. Then a second example is using a thermocouple for high temperature sensing. This is usually used for measuring exhaust gas temperature. And for these applications, normally you would use an internal temp sensor for your cold junction compensation, and then calibrate the thermocouple inside the part, and the data coming out the scent pin would be your calibrated temperature from the thermocouple sensor. So thank you for your time, and I hope this presentation offers a good reference material so you can go back and review the different protocols and terminology of scent. So thanks and goodbye.